Okay, we're at the breadboard. I don't have anything powered up yet, but I'm just going to walk you through what we have here. On the left hand side we have a 1K resistor with a 3 volt Zener and a 1N4004, I think, in series to ground. So this would add a bit of temperature stabilization. In the next circuit, and that's all there is for this circuit, in the next one, what we have is one of these J109 FETs that I mentioned, the JFET, and it's got a 10K feeding back up to the gate from the source, and it's got, I don't have any 200 ohm resistors, so what I have is a couple of 470s in parallel. It's close enough to make this work. It goes between the source and the Zener diode before it feeds back up to the gate through the 10K resistor. And then the last circuit here, which as you can see, there's just a little bit of jumping to the supply rails and there's just the chip. That one is actually a 5 volt Ref 02 device. So that's all it is. It's a little 8-pin dip. As I said, you can feed it from anything from about 8 volts right up to 30-40 volts, and it will quite happily supply you 5 volts. So that's our circuits. And just as a matter of interest, this device that's sitting up here right now is actually another voltage reference. It's a 5020 from Texas Instruments. Now the reason why this one isn't hooked up into this is because I want to be able to swing the voltages quite considerably. This voltage reference here, it will only work with up to 18 volts on it, and I actually want to take these up to 20-30 volts, so it's not in there so that I don't accidentally blow it up. And this device here, the Ref 02, will actually demonstrate the capabilities quite nicely of one of these single chip design devices. Okay, so let's just get this thing powered up. I'm just going to quickly show you the other things I have hooked up here so that you can see the whole setup, because I won't necessarily have everything pointing to the breadboard all the time because I've got too many devices to go through to show you. So let's just pan around here for a second. So the first thing we have up here is we have our signal generator. This is an Agilent 33622A arbitrary waveform generator, 2-channel, up to 120 megahertz. We're just going to use it to produce between a sort of 60 hertz ripple injection, as if it was connected to a bad quality power supply, and maybe inject 5 or 6 volts of ripple at about 60 hertz, which, you know, even a transformer with a couple of caps after a rectifier is going to be a lot better than 5 or 6 volts ripple, even at 30 volts. The device underneath it is my bench power supply. That's a professional Keithley device that was sponsored by Element 14 for me to be able to use with these projects and things. It's going to be generating our supply right now because I haven't received my transformers yet to build up an actual bridge rectifier circuit from the mains with smoothing capacitors. So I'm going to use this for the purpose of demonstrating the capabilities of these voltage references. And to be honest, using this as a stable voltage reference and then controlling the ripple from the signal generator is going to give us a lot more control and be able to simulate a bigger range of conditions for these things. So the next thing I have over here are 3 meters. So I have 2 Agilent 1272A and a 1273A. The only difference between these 2 meters is that one of them has an OLED display and one of them has an LCD. The meter on the far right hand side is actually only a basically it's a Canadian Tire, which is just your basic cheap meter. It costs about $20 or $30 or something like that, and it's got 1 digit less resolution, but nevertheless it's sufficient to be able to show us what's happening with all these circuits. And then the last thing that we're going to be using, which unfortunately doesn't give me a very good output at the low voltage range, is my oscilloscope, but really the noise floor on it is pretty awful. So we will be able to demonstrate some of the noise coming out of the voltage references, but you know, at the low end where we really between the one with the JFET and the one with the Ref02, it's going to be difficult to be able to see the difference because of the noise that's going to be sitting there on the oscilloscope. So anyway, let's just go back to the power supply right now and set that up for what we need. Okay, so I'm just going to power these two things up. Please excuse the noise. Both of these, once they get going, have some fans that blow quite a lot of wind through, so it's going to get a little bit noisier, just to let you know ahead of time. So I've already done a review on the Agilent 33622A arbitrary waveform generator, which you can find on the Element 14 website and also on my YouTube channel. The Keithley, I haven't done a review or teardown or anything like that on it yet, but I will be in the near future, so stay tuned for that. Suffice to say, for now, it's got full remote control capability. It's got 3 channels, 2 of which can go up to 30 volts. The third channel can go up to 6 volts, and all the channels can handle 1.5 amps each, with the 6 volt one being able to go up to 5 amps. So all I'm using for this demonstration is the one 30 volt channel output, and I'm going to be using set voltage here. So if I press this, you can see I can adjust the voltage just using either the dial or I can actually type in a value on the keypad. So you can set a current limit, which I've currently got set to 1 amp. I don't need that much, but that's what I'm setting. And I have a voltage voltage setting of 20 volts at the moment, because what I'm going to do is actually inject the extra 5 volts peak to peak from my waveform generator. So that's going to actually take it up to 30 volts and down to 20 volts or thereabouts. So it will be a very rough ride for something that's not very good at regulating. And the output of the power supply actually loops through to the input negative of the waveform generator, and then the positive output of the waveform generator goes over to our circuit to supply these 3 reference builds that we've done on the breadboard. The negative side goes straight to the breadboard as well, of course. So first thing I'm going to do is switch the outputs on. The waveform generator's output is already on, which is why on the power supply here you'll see it reading 332 millivolts on the output. One of the nice things with this Keithley power supply is that if your outputs aren't actually on, it will act as a basically 3.5 digit multimeter as well, up to the range of about 30 volts, and it's fairly accurate, 0.03 or 0.05%. So if you're doing some testing and you're actually short of a couple of multimeters, and you've got something like this, you can actually use a couple of the inputs to display the voltages too. Anyway, so I'm going to turn the output on now. So that's outputting 20 volts, and you can see on here, hopefully, it's actually consuming about 25 milliamps. So just zoom in a little bit and you'll be able to see that. So if you look down here, right here, you can see it's actually outputting the 25 milliamps there. That's all that's being consumed by all 3 circuits. Okay, so now I'm going to move across to the meters and turn these on, and you'll be able to see what we're outputting here. Excuse the beeps. I have one of these that I need to adjust. The third meter is I've got a 8 volt Zener in here right now, and I want to make them as close as possible to each other. So I'm just going to pull out the Zener diode, and I'm going to put in another 3 volt one, so that the first 2 circuits are the same, with the exception that one has the JFET in it and one does not. So let me just drop that back in, and we'll be all set to go. In just a moment. Okay, so that's back in there. Let me just clip the multimeter back up. It's reading 0 volts right now because it's not hooked into anything. A little bit too many clips and things here. I have to get some better probes. Okay, so let me just zoom out a little bit so you can see all of them together. now what we have is the meter on the left is reading the Ref02, which was the single chip device. Now it's reading off right now because I'm actually feeding it 1 megahertz of noise, 1 megahertz sine wave at 5 volts peak to peak, which is an awful lot of supply noise, and it's not quite handling it. If I actually take the jumper off the generator and just short it together, you'll see that the voltage becomes more accurate to the 5 volts. So it's sitting at 4.997, and it'll stay there for the duration of this test. The second meter is connected to, let me just follow the wire through here a second. It's connected to the JFET circuit. So this one, when we start doing our testing, should not vary at all, ideally, as I vary the supply voltages. And the last one, which is the Mastercraft meter, is connected to the 3 volt Zener through a 1K resistor. Now it's reading a little higher because remember these also have the 1N4004s in series with the Zener diodes. So that's why there's a little higher voltage, but that's okay. We're actually looking for how stable the outputs are, not for the absolute accuracy of these Zeners. Although if you really want to see, before the end of the video, I will hook them up individually to the supply so that you can see it. So this has got no noise on it whatsoever right now, and I've got 20 volts applied. So you can see we've got 4.997 from the Ref02, we have 3.47, and we've got 3.57 respectively. So the one with just the 1K resistor is sitting a little bit high. Now if I increase this, and if I just before I do that, I'm just going to feel the components here. So even with 20 volts right now, I've got a quarter watt resistor, and it's actually already getting quite warm, because if you think about 20 millivolts flowing through into 3 volts, that's actually 20 volt supply, so I'm putting 17 volts at 20 milliamps, so that's about 300 and odd milliwatts that's being dissipated in that quarter watt resistor. So it's already starting to get warm, which, as I've mentioned before, temperature is not your friend when it comes to voltage references. What I'm going to do is I'm going to increase it up to the maximum for this channel of the power supply. So right now it's 20 volts, so I'm going to increase it to get the right range, so I do a volt at the time. So that's 21 volts. You can see I'm just going to flip between 20 and 21. You can see the first one, the 4.997, is not budging at all. The middle one, which is connected to the JFET, is not moving. But the last one there is actually going from 3.57 up to 3.6. So it's actually jumping quite about 30 millivolts, 25 millivolts, just from a 1 volt change on the input. Now if I go up to making a 5 volt change here, you can see I'm going down to 20. So I'm at 20 volts again. You've got the 5 volt output is staying rock steady. The JFET output at 3.44 is staying rock steady. But the one that just has a series resistor there, you can see that if I go up just 5 volts, I've gone from 3.57 volts and I'm going up to 3.68. So I'm increasing over 100 millivolts on the output of the one that just has a series resistor. And if I take it all the way up to 30 volts, then it's gone up yet another 100 millivolts. So if you've got a variation on the supply, you can see you can have quite a considerable swing on this first resistor Zener combination where there is no current limiting circuitry built in. If you look at the middle one now and focus more on that, and I'm going to go back down to 20 volts, see it's sitting at 3.444, and as I increase it up to 30 volts, it's sitting at 3.448. So it's changed very, very little. That's back down to 20 volts, back up to 30 volts. So it's changing a few millivolts on the output, but within the range of this, if you're talking about the 3.5 volts, it's not changing more than 0.1% of the output there. which is, you know, for most power supplies that you're going to be using, that's probably okay. So 3.445, and it's going up to 3.449. So 4 millivolts out of 3.5 volts. It's not even 0.1%. The last one, of course, is, you know, it's changing, as I said before, 3.5, 8, and it's going right the way up to 3.77, so 200 millivolts, with a swing on the input of about a 30% increase from 20 volts to 30 volts. So that's not very good at all. Now, obviously, a power supply is not going to be having its supply rail swinging this much. I'm exaggerating this so you can see the difference of the 3 different regulators as far as the stability is concerned. And I'm doing a big voltage swing so that you will actually see the readings changing on the meters for the range you've got. You know, in a real system, the voltages are not going to change that much, but if you increase the load, they are going to change a little bit, and that will be reflected through any gain of amplifiers and feedback circuits that you may have that this voltage reference is connected to. So obviously, the more stable the signal, the better as far as that's concerned. Now, what I'm going to do now is I'm going to start introducing some noise to this. So we've already seen that these circuits will stay reasonably well. I mean, except for the one that doesn't have any current control on it, but it does not handle changes in voltage very well. So the next thing we're going to do is introduce some noise. So I'm just going to reconnect in my Agilent arbitrary waveform generator. So I've just plugged it back in now. It's still outputting the 1 megahertz. I'm just going to reduce the frequency down to a more reasonable frequency of, you know, typically you're going to get something like 60 hertz noise. So I've just changed that to be 60 hertz, and you can see immediately that the 5-volt supply has gone back to its nominal 4.997 volts. The constant current one is sitting at 3.47 volts, and the 3.54 is, you know, they're all basically ignoring most of this 5-volt peak-to-peak signal that I've put on here. I'm just going to put the oscilloscope on so I can actually show you what the supply is doing with this. So let me just zoom out a little bit so that you can hopefully see the oscilloscope as well in the bottom right corner there. Bring them all into view here. There we go. I think that's good enough. So let me just get the scope probe here, and fortunately I have a common ground for all of these, so I can connect the scope probe quite easily to this. Give me 1 second. Okay, so just connecting the ground, and if I'm going to connect this to the supply first of all. So I've got why am I not seeing noise on here? 20 volts connected, and oh, my frequency is way too high. Okay, so that's sitting at 1 volt per division on my oscilloscope. I have it AC coupled because otherwise it would be off the top of the screen. You've got 20 volts DC feeding into the supply here, and I've got 5 volts peak to peak at 60 hertz superimposed on top of that. Now if I I'm going to first of all measure on the Zener diode that does not have my meters are just shutting off in case you wonder what that noise is. Let me just turn one back on again. Okay, that should keep them from going off for a moment. So this is on the output of the Zener and resistor pair, and you can see here even at 1 volt some of that ripple is actually still showing through, and if I increase the resolution of my scope down to 50 millivolts per division, you'll see that there's basically 1, 2, 3 divisions, so 150 millivolts of that 5-volt swing is actually getting to the output of the Zener diode, and that would actually be amplified and start showing up on the output of your power supply if you had this sitting there with that much noise on your rails. Now I'm going to take this one off, and now I'm going to move to the Zener diode that has the constant current circuit connected to it, and the spikes that you can see here are actually the noise of the oscilloscope. If I disconnect the power supply completely just for a moment. Oh, now I've got the back feed of the, let me just turn the supply off instead. Turn that off and turn off the signal generator. I just want to show you that the noise on the oscilloscope you see there, it's no different to when we had the things turned on. So please just ignore that. I really can't do anything about it. It's just the scope that I have. So now I put the power back on. It's 20 volts. It's got 5 volts peak to peak noise. Sine wave at 60 hertz being superimposed there. So you can see that the second one with the constant current, little bit of circuitry, there's no noise being superimposed there that you can see. I've just increased this to my maximum resolution on the scope. You could see a little bit of ripple showing up on the output of that, but there's really not much there at all. I don't know if I can put a bandwidth limiting is already turned on this thing, so there's nothing much else I can do to improve that signal. Now let me just connect to the last one, which is the Ref02 single chip circuit, and I'm going to connect close to the chip if I can here, so that I don't get incorrect noise. Okay, that's connected there, and you can see that there's actually, it's very tough to see maybe on the camera, but there's just a little bit less noise showing up on the output of the Ref02. I actually can barely see any ripple caused by the input oscillations on that. You know, it's just the oscilloscope with its noise floor showing through. So that's the 3 circuits you can see. So that's, you know, going back to the Zener circuit, you can see a little bit of ripple showing through there, but not much, and that, you know, that's pretty good. And going back to the Zener without the constant current regulator, you can see that is really got a lot of noise on it. That's going full scale top to bottom of my oscilloscope. Now let's see what happens if we increase this the frequency of the noise, of the ripple that I'm putting on here. So right now it's 5 volts peak to peak. I'm going to change the frequency up to maybe 1 kilohertz output. You can see the Zener diode with just the constant current, without the constant current, it's just as noisy. Let's just flip to the next one. Alright, that's still about the same as it was. It's barely detectable, and the Ref02 is the same. It's not really being seen at all there. So let me just go back to the first circuit again, which is the Zener without any constant current. I'm going to jump it up to 100 kilohertz now. Okay, so now we have 100 kilohertz at 5 volts peak to peak. My oscilloscope range has gone out of whack. I need to just increase this. It's a weird effect of sampling oscilloscopes that they will show you funny things if you've got them way off the frequency that you're trying to measure. So you can see the Zener diode without constant current, even at a 100 kilohertz, it's still getting through to the output. If I go to the next circuit, which has got the constant current source, this one is now showing up, 150. So if I go back to 60 hertz for a second, all right, 60 hertz, it's not coming through with the JFET. When I go up to 100 kilohertz, this one is now showing through the higher frequency noise on the output. So we're starting to reach the limits of what the JFET, without any compensating capacitor feedback or inductors in the circuit, can handle. We're going to go up a bit further in a moment to a full megahertz and see what happens. But let's just go and check the output of the Ref02 again. Just getting hooked on there. Alright, so that one is also showing now about 20 millivolts of noise. So it's starting to be affected by the supply noise. Now I've got some capacitors here, so what I'm going to do is just put a, I think probably around about 47 nanofarads. I'm just going to connect that across the supply rails and see what happens with the noise. Just 1 second while I try and plug that into the breadboard. There. So that didn't make a lot of difference at that frequency by putting that capacitor in. Let me put an electrolytic right by the supply instead and see if that makes any difference. Okay, so I put an electrolytic in there. This one's about 4 or 5 microfarad. Let me just check what it is. It's 4.7 microfarads electrolytic, and what it seems to have done is actually made the noise worse. If I take that out, all right, so what it's done is it's actually making the yeah, it's making things a lot worse. If I try and put this on the output of the reference instead to ground, let me just try that now. If I can get this to plug into the breadboard and put it in, that actually has managed to kill the noise, at least significantly anyway. See if that will actually do the same thing for the Zener output. So let's move that back to the Zener diode with the constant current. And we'll put a capacitor across from that to ground as well. Just try and get these things hooked in here. Okay, so that's made a significant difference on that too. Take it off. So what I'm watching as well is what happens to the voltage on it. So as you can see there, that's off and that's on. So it's killing the noise, but it's not actually changing the voltage by anything more than about the last digit on the meter. So that's pretty good. And the last one, it's probably still going to have an effect even on the last one, because what we're really doing is effectively shorting out the AC noise from the generator. So that's killed it right down as well. All right. So if you do have a noisy supply, obviously putting a small, a few microfarad capacitor on the output of your VREF will improve its noise immunity quite considerably. All right, but let's just continue this without any capacitors on there, so we know that that's going to be causing a problem. Now I'm going to increase the frequency to 1 megahertz, and we'll see what happens now. So the one that's still in the scope here is the let me just get that triggering properly. There we go. So now we're sitting with a megahertz signal, and if you look at the voltages, the 5 volt Ref 02 has actually dropped its output voltage quite considerably. The two Zener diodes, though, they're still sitting pretty close to what they were. I'm just going to drop it back to 60 hertz in one sweep to see what happens. You can see the two VREFs using Zeners did not change one little bit. Now just go back to 1 megahertz again. But the noise immunity of the Ref 02 is actually, it doesn't like the 1 megahertz signal. Now you're not normally going to get that kind of noise in your circuit anyway, or very, very rarely. You're going to have some decoupling capacitors and things like that to try and help out. If I go back to the this is the constant current one, you can see that without any capacitor protection, that one's even worse now than the one without any constant current regulator. And the reason for that is the JFET is probably gone beyond its bandwidth capabilities, and is now, the capacitance of it is allowing the 5 volts peak to peak 1 megahertz signal to just blast straight through it. I would imagine that it's maybe something might even be getting warm, but I can't feel it with my fingers. Now if I just put this back on the Ref 02, you can see that's behaving quite strangely on the oscilloscope there. So I'm just now going to put the capacitor back on its output and see if that cleans it up. So that certainly has cleaned it up a little bit. And if you look on the display though of the meter, the left one, it's still sitting at 4.988. It's not changing that, so it's not enough to fix the problem of that one. If I put it across the supply with the capacitor at this frequency, maybe that will help. Let's just try that now. Just dropping the capacitor in across the terminals. So there, that's actually improved the voltage output, but it's actually also increased the ripple that is showing up. So I'm just putting this big capacitor across the supply rails of the RefO2, not the output of the RefO2. And that's made quite a considerable jump in the noise there. If I take that one out and now just put the small decoupling capacitor across the supply rails, it's probably going to also help because of the frequency we're dealing with. Yeah, so that's come back up again. But of course, you've still got this 100 or more millivolts on the output ripple. So if I put a capacitor on the output as well, we'll probably find that it cleans it completely up. Yeah, it's certainly reducing it quite a bit. Now, of course, for all of this, some of the noise here is going to be getting generated by the breadboard. They're not the best of things for decoupling and noise immunity. If you were having this on a proper PCB to do the same thing, you would not be getting, I don't think, as much noise from these circuits. But you can see here now, though, we've gone through 3 different kinds of voltage reference, from ultra cheap to, well, just cheap, because I mean none of them are more than just a few dollars to make anyway. But at high frequency noise, the better voltage reference is actually very intolerant of that ripple. Now, as I said, it's a huge amount of ripple. I'm putting 5 volts peak to peak at a megahertz now into the supply rail. If I actually drop down the amplitude of this, it's at 5 volts. Let me just take it down to 1 volt perhaps peak to peak. All right, my outputs now, they haven't changed, except that if I remove the decoupling capacitors, that one and the other one, right, they're both now back out of circuit. I've got 1 volt peak to peak at a megahertz being injected onto my supply rail. I do have a little bit of noise, but as far as my output is concerned, it's exactly on the money of where it's supposed to be. Now, if I take this back down to a reasonable amount of frequency noise, sorry, need to go cancel parameter frequency, go back to 100 kilohertz. All right, it's just completely ignoring that, and most of the noise has disappeared from these circuits. All right, and as I said, I have not put any decoupling on the end of this, so we're coming from the power supplies on the bench over all these wires, and we're going in. So this is really the worst case scenario that you could imagine. But I think it does nicely demonstrate what happens with noise going into these different reference circuits. Personally, I think with a reasonably good power supply, the RefO2 is still probably going to give you the most accurate and stable voltage for all of them. But if you're not using an A to D, D to A converter in your circuit, and you're just going to build yourself a regular analog one, then clearly the one with the constant current source using a JFET works just as well, and it's just as stable across pretty much the whole same range. And it's certainly going to be as accurate as you need if you're going to have a pure analog bench power supply. So that's the second check we've done. We've covered what happens when you increase the voltage, the DC voltage on the supply, varying it between 20 and 30 volts. We've had a look at what happens when you inject some pretty bad ripple onto the power rails, and we've seen how that happens. So what I'm going to do is I'm actually going to take the signal generator back out of circuit again here. I'm just going to take it straight from the power supply now. So things should settle down quite nicely. I'm going to turn the signal generator off for the noise. And what I've got here is I have a hot air gun, right? And what I'm going to do is I'm going to heat up the Zener diodes and the RefO5 of each of these. And what I want you to do is keep an eye on the digital multimeters for each one. I'll tell you which one I'm heating as I do it, and you'll see the effect that a bit of temperature will have. Now, unfortunately, the Zeners that I've got, the temperature coefficients don't match the 1N4004s that I have in circuit, so I won't try and show you the difference of having the compensation in, because it's just not going to do it. But what I will show you is the effect of heat on these Zener diodes, and then I will also heat up the Ref02 certainly to beyond the point where I can even touch it, and you should hopefully see that it's going to be rock steady. So I'm going to turn on the blower now, and it's set for 280 degrees centigrade because it's actually a hot air soldering gun. So this should be able to demonstrate quite considerably. I can't hold my hand in front of it already. So the first one I'm going to do is the one that's sitting, let me just zoom back in again on the meter so you can see a little clearer. I'm going to be heating the one that's connected to the Mastercraft, which is the smaller meter on the right hand side here. All right, so it's sitting at 3.576 volts right now, and I'm just putting the heat on now. All right, look at this, it's just actually going down, so it's demonstrating a negative temperature coefficient down to 3.3. I don't know whether I'm going to kill it or not by heating it up too much, but 3.31. Yeah, that's I think I'm just killing it here. Can't touch it. So it went down to 3.3 volts with a bit of heat from this heat gun very, very quickly. Yeah, I can make that go down quite considerably, 3.3 volts. And that was sitting before at about 3.5 volts. Now, the next one I'm going to do, I'm just going to let that one settle down again. I'm going to heat the one that has the constant current generator on it now. And you can see that the temperature, even though you've got the constant current circuit, it's still affecting it with a negative temperature coefficient, which is going down. All right? And that you don't want. I mean, I don't know what temperature it's getting to, but it's certainly getting too hot to touch. And you know, inside a power supply, if you're drawing a lot of power through at a low voltage, you are going to be generating a lot of heat. So if you're in that situation, you might want to include a fan. If I just go back to the first circuit again, I'm going to heat up the 1N4004. All right, and you can see that one's actually got a negative temperature coefficient too. So it really would actually make things worse if you had it in circuit as well. And I'm going to heat up the one in the second one. All right, so those are no good for this because the Zeners have got the same temperature coefficient as the 1N4004 diodes have. So, you know, don't do that. Now, what I'm going to do now is I'm going to heat up the Ref02 to the quite considerably. And if you look at it, it's sitting at 4.998 volts right now. I've just applied the heat to it. And I've got the hot air blower about ½ an inch away from the chip. It's gone up 1 count at the moment. And this thing is already, I'm just concerned about melting my breadboard here. No, it's actually just dropped back down again. So it's starting to go down, but ouch. That thing is so hot, I would probably be melting solder on the pins. I got to make sure I don't melt my breadboard. So I've just taken it off, but you can see that is a huge amount of heat on that Ref02, and it made pretty much no difference whatsoever to the output voltage of it. I mean, it fluctuated 1 digit, but that could just be the meter or anything else in the circuits that it's affecting it. It might even be the fact that I'm heating up the metal and the connecting wires around the circuit. So from a temperature stability and a voltage stability for the voltage reference, the Ref02 wins hands down. Both the Zener diode based ones, they fail miserably when they start getting heated up a lot. And of course, from a signal immunity at the lower frequencies, the Ref02 also wins, but as you get to high frequencies, the Zener with just a resistor, which surprised me, actually starts to win out. The other two start to break down because of the other devices and the capacitive effects of them up at a signal, you know, a ripple of about 1 megahertz, which could be coming from, you know, switch mode power supplies or anything like that. Anyway, so I think you can see now that with voltage references, how they get affected by different sources of environmental noise, temperature, and voltage fluctuations. You know, if your mains is going up and down and you have a regular transformer, even a toroidal one, then the output of the transformer is going to go up and down a little bit. That's going to affect the supply that is feeding your reference. And so if you don't have constant current or some other kind of control mechanism to keep it in check, the reference voltages are going to change. So I think, you know, depending on how you move forward with your circuit as we do this, you can pick whichever reference you like. And the way I'm going to build my boards up is I'm going to have a little daughter board with the reference circuit on it, maybe with a little 3-pin connector. And what that will allow me to do is easily unplug one voltage reference and plug in another one. So if you're building this up on Breadboard or something like that, which is perfectly fine for what we're doing, I suggest that maybe, if you are going to go with just a Zener diode circuit, build it on a little bit of Breadboard as a daughter board, and then simply plug it into a connector onto your main board, and that way you'll be able to upgrade it or change it and try different things out as you go through the project. All right, anyway, I think that pretty much concludes what we're trying to do here and what I wanted to demonstrate to you as far as voltage references are concerned. I think the next stage we're going to do is deal with the op amps and the voltage control circuitry. So we will keep one of these VREFs on the breadboard, and I will add an op amp circuit to this, and we will look at how we can control the voltages in an analog way coming out of the op amp. Now, to start with, we're not going to have a power stage. We're just going to have the op amp performing some control, but then we're going to add a just a low voltage, low power driver stage. I don't have any heat sinks yet, so we can't do any heavy duty loads, just to show the closed loop nature of voltage control. And then the one after that we'll do the current control, and follow that on with hopefully by then my components for the power stage will have arrived. We will do the driver stage using shunt resistors to detect current, and we will also look at the actual main power reduce circuitry and rectification and smoothing from the mains down to the main 30-volt supply. But for now, this is the voltage reference quick tutorial done. I hope you learned something from it. I hope you saw the benefits of the different circuits and the disadvantages. And now you just need to go play with it yourself, try a few things out. As I said, these are just 3 variations of deriving a voltage reference. There are many, many more. Google is your friend. Go have a look. You don't have to use the circuits I'm using. You don't have to use the chips I'm using. Just decide on what voltage reference you want to use. As I said, it's not important what the value is. What is important is that it is stable. And then if you're using or plan on using a digital to analog converter, analog to digital converter to automate the power supply and have a microcontroller involved, then you might want to look at one of the references that are set to handle an A to D, D to A converter. So before we close off, what I'm going to do is I'm going to take you to my computer screen, because I want to show you the characteristics of the Zener diodes. So the first one we're going to look at here is, let me just bring it to this screen over here, because I think it will be a little bit easier. Okay. Hopefully you can see that well enough. What I've got on the screen at the moment is the circuit that I showed you that was on a little daughter card. That is the Ref 5020 from Texas Instruments. I'm just going to increase the size of the screen so that perhaps you can see it a little easier. So these circuits, you can get them, they're all in these little SOT6 or SOT8 packages, so like 8 pins. And you can see the Ref 5020 is a 2.048 volt reference. Then you've got a 10 volt reference, a 2.5 volt reference, a 3 volt reference, a 4.096, and a 4.5 volt reference. The temperature coefficient, this is parts per million per degree C. So you can see this is 2.5 parts per million. We were seeing, parts per 100 when we were heating up the Zener diodes. When I heated up the Ref 02, you saw that it changed the least significant digit, and I don't think that was even due to me heating it. But you can see these devices, they're the same temperature coefficient all the way across the board. And even the maximum temperature coefficient is only 3 across the board. So these are extremely stable. The reason I didn't put this one into my circuit is because down here you'll see it has a maximum voltage rating of 18 volts, and I wanted to be able to run this up to the supply rails that you would typically see in a power supply, so 30 volts, and I was just putting lots and lots of noise on there. And you can also see with these that they take very little current, typically 800 microamps, so just under a milliamp for driving these things. Now if I bring in the Zener diodes, on the other hand, in here, let me just shrink the screen so you can read it. This one has a table, so they're 500 milliwatts, which are the ones I was using. They have a D rating of about 4 milliwatts per degree C as you heat them up. Remember I mentioned that the forward voltage of a diode, this is at 200 milliamps, this is about 1.1 volts, but that's in the effectively the reverse direction that you'd be using as in a diode anyway. So looking at this thing, the temperature coefficient here is this column here is what you want to look at, and you can see that with a 2.4 volt Zener diode, it's got a negative 85 millivolts per, sorry, it's percent per degree C, so it's 0.085% per degree C. Now I was heating it up considerably, and you saw that they were changing quite a lot. And I see the low voltages here up to 2.4, 2.7, 2.8, 3, 3.3, down to 3.9 volts. They're all with a negative temperature coefficient. When you get to 4.3 volts, it's actually sitting there plus or minus 55 on the temperature coefficient. So it's sitting around that nominal 0 volts per degree C kind of temperature coefficient, which would be ideal. So a 4.3 volt one, it's still going to have one plus or minus, you're just not going to know what. If you want to have better control, then you might want to go down to one of the lower value Zener diodes and make sure you have a determinate amount of temperature coefficient, rather than not knowing which way it's going to go. And that way you can find an equivalent diode to compensate for it. Now what I had is a 3 volt Zener diode, so it was literally one of these NTE 5004As, and it has a minus 75 temperature coefficient. If I actually went and put in a 5.6, I don't actually have one, then that has a plus 5.1 or 5.6, something up there. It has a positive temperature coefficient. So if I put that in the circuit with one of the 1N4004 diodes, it would have been able to at least compensate for some of this temperature drift and flattened out the heating effect of the circuit. And as as I start going up in voltages, I'm up to about 20 volts now. You can see I'm back up to the 86, like 8.6, I think, I'm not sure if it's percent or 0.086% temperature coefficients per degree C, up to almost the 0.1% per degree C. Now you got to remember, I was heating these things up to well over 100 degrees centigrade. So it again was extreme because I wanted to demonstrate what happens. But no matter what, the more stable your circuit is, the better that your overall system is going to be. Now the next thing I wanted to show you is let me just minimize this, is the, where is it, this is a typical circuit using a RFO2. So it's feeding at 15 volts, it's got a 5 volt output, and they're feeding this straight into a digital to analog converter. And this circuit is actually, this analog to digital to analog converter is what I'm going to be using later on through the tutorials. This actual sheet here is actually for the D to A converter, not the voltage reference. So this sheet here is the N-channel silicon junction FET that I'm using. So it's a J109 is the one that I have. You can see it's a little T09 packaging, and it's got about an 8 ohm hard-on resistance for the J108. It's a little bit different for the 109. If I scroll down to the actual data sheet, what you're also going to see here is the voltage for what they call gate source cutoff voltage. So if you bring the gate negative with respect to the source, and if you remember our circuit, the source is the one that's more negative of the drain in the source. The drain is actually going to the positive supply rail. you need about -6 volts, somewhere between -2 and -6 volts. And if you pick your resistor, which I had about 230 ohms-ish in the circuit, so you can just do Ohm's law and figure out the current that will be flowing through it to get the cutoff voltage to take effect. Now, we don't want it to cut off, obviously. What it's going to do is it's effectively going to self-stabilize into a constant current generator. So you may have to play around with the resistor to get a sufficient current to flow through it to stabilize the Zener diode a little bit better and to bring it into the region or the voltage to be more accurate to what you're desiring. Because not every Zener, they've got a certain tolerance on them, so you may have to tweak things to get your VREF to be accurate. Yeah, so that's the FET there. I'm just trying to find if I have the sheet for. Oh, there we go. Just bring this one over. This is the Ref 02. All right, it's made by Burr Brown, but it's also obviously they're owned by Texas Instruments, and it is a very, very good voltage reference. And the nice thing is the huge supply voltage range that you can feed into it. We're planning on building a power supply that has a main rail of about 30-35 volts. So this thing will work from anything from 8 volts all the way up to 40 volts. And one of the features of my power supply that I'm going to build is I want to be able to throw a switch and put my transformer windings in parallel to give me twice the current. But what that's going to do is it's going to reduce my main supply rail from 35 volts down to about maybe 18 volts. And you've seen what happens to the VREFs when you start messing around with wild swings on your main supply. They completely change and therefore would throw out your accurate control of the output stages. So this will work from 8 to 40 volts nicely. Has very little current flowing through it. Its load regulation is 0.008% per milliamp. And its line regulation, which is where we're varying the supply rail, 0.01% per volt change. But that's what it claims here. But what we actually saw was it's not even that much of a change, okay, which was really, really good. Low noise. The temperature stability is 10 parts per million on this one. Now, if you remember the 5020 that we had up, let me just bring that back up on the screen again for a second. So this one is got a temperature stability coefficient of 3 parts per million per degree C. The Ref 02 is not quite as good as that. This one is sitting at, where'd it go? I lost it. Oh, there, 10 parts per million. So it's about 3 times less stable over temperature. But as you saw, I heated it up considerably and it made no difference on the output. So even though it has this as a worst case, typically you're going to see it to be a lot more stable. But if you want to guarantee it, then go for something like the Ref 5020 or 5045 or something like that. And the only penalty you'll have to pay there, and it's only a small one, is you'll have to supply your analog circuitry with a separate supply to the output of the power supply, which was going to be your 35 volt rail. You're going to have to create something like a 15 volt rail for your op amps and things, which actually isn't a bad thing overall. Yes, it's more expensive, but your op amps, a lot of the ones you'll see, you're getting very, very close to their maximum voltage capabilities. Even the JFET that we were using actually has a maximum voltage of about 25 volts. Now we had 3 volts odd across the Zener diode as well, plus the 1N4001. So we were probably working right on the limits of its voltage range. And if you wanted to go higher on your power supply, then that JFET wouldn't work for you. You'd have to find one with a bigger range. And the same thing applies for the op amps that we're going to be using. If they don't work for the voltage range, you're going to have to do something about it. Either you're going to have to buy more expensive ones, or you can choose to supply your analog control circuitry with a lower voltage. And a lot of transformers will have like plus or minus 12 and plus or minus sort of 30 volts or plus or minus 15 volts as well. So you can choose to tap off the windings and get a lower voltage supply rail to drive that extra circuitry. And if you look at this is a toroidal transformer that I'm going to use for my analog circuitry, and what this one has is a plus or minus 12 volt output at about 1 amp. Something like this, it costs about $30 from Element 14, and the nice thing is this would actually make a good transformer for a lower powered power supply, because it's got your plus or minus 12 volts, so it's going to give you maybe 24 volts, and it's going to give you that at close to an amp. So for a lot of sort of school projects and things, that's probably more than adequate for what you would need. And right now Element 14 have these on their site at a discount, especially for these ones, because I think maybe the company's not going to make them anymore or something. Look for the ones with a little red star next to the prices. Those are ones that have been reduced because they're going to be discontinued or something. Anyway, I think I've pretty much covered everything as far as voltage references are concerned, and the effects they can have on systems with, temperature stability, supply stability, noise stability. I think that pretty much covers it. So I'm going to wrap up now because I've probably been rattling on for about an hour. I'm glad, I hope you find the video useful, and I hope you stick with it for the rest of the course. So we'll see you on the next video. Thanks.